So, today what we do is we continue, instead of writing a polynomial through the set of points, we decided that what we will do is we will go with constant velocity for some duration and then go with constant acceleration for some duration, then go with constant velocity and then again come down with constant acceleration. And so, the position looks quite smooth, the velocity looks continuous, is continuous, but then the acceleration has discrete jumps because you go with constant acceleration, then 0 and then again a negative value. And then so we discussed that this is obviously giving a time interval and a motion to be covered, and it is specifying the velocity. Usually specify the peak velocities of each joint and then give the input as a percentage of the velocity. So that guarantees that the motion can be carried out. And finally, usually you take initial final velocities to be 0 starting from rest ending up at rest, then you get a symmetric trajectory with respect to the midpoint qm. So given that, the task is we are trying to derive the polynomial. So these are the basic parameters. So we are going to accelerate till Tc, and so the joint angle at this value is qc, the velocity is qc dot, and this velocity is maintained over this period of time and then it comes down. Now after this, it is essentially a matter of just solving s is equal to ut plus half at squares and equations like that. So if you have a constant acceleration here, this multiplied by Tc gives you the velocity at this point, and this is the velocity. If I take the q value at Tc and the q value at the midpoint, which is qm, and divided by the time interval, I will again get the velocity. So essentially equating that these two velocities must be the same, and then using the fact that the velocity at time t equal to 0 is 0, then this is s is equal to ut plus half at squared basically. And so you can combine these two equations, you eliminate qm and you get equation in this form. Now this is a polynomial in Tc. So you are trying to solve that what is the Tc given some qc dot and these parameters, what is the value of Tc. So this is a quadratic which you can obviously solve for Tc. Now when you solve it, you will get a plus minus sign here. Now, so there are a couple of things which are of interest here. So even though there are two possibilities here, you can eliminate one of them, because Tc has to have a limiting value. It cannot be more than Tf by 2, right, because you are accelerating over the. So essentially one solution that you get is this Tf by 2 minus something, other solution you get is Tf by 2 plus something, right. So you cannot obviously have this solution that you eliminate because of the physics of the problem. So you have a unique solution for Tc which you can solve for, and so and then the fact that qc that acceleration essentially has to be in the direction of qf minus qi. So you have a final position and you have a initial position, your acceleration generally initial acceleration has to be towards there. On the other hand, if qf is lower, then it will be a deceleration. So that is there. So using these parameters, the square root becomes unique, and so then there is this term which is interesting, which is 4 times qf minus qi divided by tf squared. So this is a limiting value, and So if you have exactly this value, if you have QC double dot equal to this, then there is no constant velocity segment. Okay, so what happens is, then through the whole phase you just accelerate, then you decelerate. Okay, so that's a thing worth noticing. So you get the triangular profile, and in general the acceleration has to be more than this limiting value, because if it is less, then you cannot accelerate and decelerate, and that is the faster way of doing that. Then we will not complete the motion in the given amount of time. So this is quite simple, right? There is nothing great about it except this convenient formulas and eliminating one sign of the root, and just being aware that there is a limit to it. So finally, if you know Qi, Qf, Tf and the acceleration, then you get Qt in this form between 0 t Tc. This is constant form. So only thing is, here you are writing everything in terms of these parameters. So just 4 parameters, so you can take it in as input and you can write the terms out essentially. Then you write it into a hardware and you are done. Now the other thing is, you can also limit the velocity. So the cruising velocity, the flat part of the trapezoid that we are talking about. So again, you can quickly figure out that cruise velocity is subject to this constraint Qf minus Qi upon Tf is equal to 2 Qf minus Qi upon Tf. Okay, what happens if it goes the other side? If it goes leftward? If this is not satisfied, then?
It will not reach in the time Tf.
It will?
Not reach Qf.
Not reach. And if it is this? Asking for too high a velocity, right? It will cross. You can't have you basically have a 0 constant velocity phase. So you have to then, this is outside feasible ranges. So then you essentially write up these equations, you get a new expression for Tc, and then this leads to a new expression for Q double dot C based on constant velocity. So now that this is specified, Qi, Qf is known, Tf is known, Q dot C is known, you can recalculate the value of Q double dot C, and then you can just use the earlier formulae. So it is a small variation, except that you realize that this is the limit. So there are limits on both sides, so based on that you just recalculate Q dot C and you can use the previous formula, or you can just rederive the equations given these 4 parameters Q dot C, Qi, Qf and Tf. Okay. Now the interesting part is, this is simple, okay, because you just have trapezoids and straight line linear connecting together. So if you look at this tau squared integral over that period as the parameter, you can show that there is roughly a 12.5% drop in the performance. So there is a price to be paid for simplicity and ease of computation. So you have a trade off which you need to work on. So what we want to then work on today is motion through a sequence of points. Okay. Now so idea is that if there is a area of the curve where you expect obstacles and things like that, you might want to specify points with more density in that area. So it is not uniform, so you will have more number of points in that area. Similarly, if you have high path curvature, you might want to give in more points, because that will give you a better approximation of the curve locally. If you have low number of points, then there is a problem. The catch is, every time we generate one such point, we are usually doing inverse kinematics, unless we are using a teach pendant. So you have to, somewhere down the line you have to compute more if you are putting in more points. So you try to work with the minimum point set. But if we have to do it, then we put in more points. So, the problem is to generate the trajectory when n points are given. These are called path points, you would call them path points, and they have to be reached by the manipulator at certain instants of time. So, specifying time and when you get to this path. Now, at each joint variable, for each joint variable, so since I am using n points, these n points will have a corresponding value at each joint. So, I will have n constants that each for each joint. So, there will be n values of theta where I have to go to. In this case, we are calling it q. N values of q where we have to go to at specified time intervals. Okay. So, simplest is to use a n minus 1 order polynomial. The catch is if I use n minus 1 order polynomial, I can make it pass through all those points, but I cannot control the initial and final velocities, which is not a good idea. I need to say you start from rest or you start with this velocity, whatever. I mean, that depends on the problem that I am working on. I should be able to specify that. But there are other problems also. Now, as the order of the polynomial increases, the oscillations will increase, right. So, it will start wriggling through those points. It will go through these points, but it will start wriggling around and you can't control them. So, even between 2 points, I am showing a good one, that if you have point here, point here, point here, you could go like this, but you could also go like this through them. So, the number of wriggles where you have how many peaks and this thing you just cannot control. And not only that, it is also difficult to solve if you have large number of points n approaching 50. Solving for a 50th order coefficients of a 50th order polynomial is not easy, even though you can write it out. And so there are other couple of problems which are written there is, so there is numerical instability, difficult to solve, and the coefficient depends on all the assigned points. So, you change one, you have to recompute everything, which is obviously not good. So, the idea is that you use multiple low order interpolating polynomials, but we will insist that they be continuous at the path points, and this is called a spline. Okay, so, you start blending. So, idea is that, so when I have these points 1, 2, 3, I mean going to n, so I have a polynomial between here and here, another polynomial between here and here, and so forth, and I will make sure that it passes to this point and the velocities are the same at this location. Now, this is a bad example because it would seem that the velocity is nearly 0 here and 0 here, but that is not necessary. So, I have just blended it correspondingly. Okay. And you can show that, well, basically if you have cubic, then I am left with 4 conditions. Okay. And so, I can ensure that the velocity here is matching. Okay. And then I want to say, for example, I am specifying not only q1, but I want to specify the derivative here and also the derivative at the final point. The problem is to find the polynomials, number 1. Number 2 is, unlike the pick and place case, right, point to point thing, I have intermediate points. Sometimes I will have these points, but do I know the velocities here? Sometimes yes, sometimes no, depends on how much you want to specify. So, the user might want to specify derivatives at each of these locations. Sometimes you do not want to specify, so just go, do not ask me, just go there. I am not bothered, just find out something nice and go. So, that is also an option. And sometimes you might say that I also want the second derivative to be continuous at that point. I really do not care what the velocity is, just make sure the second derivative is continuous, I do not want a jerk when you are moving through that, velocity you take care of. So that could be a third condition. But I mean, you can do one of them. You cannot do all three. So one of them. And finally, you could also be interested in polynomials less than order 3, which may not exactly pass to those points, but will go close to those points. That also could be an option. You said, I mean, third order polynomials is a problem. Okay, interpolating is a problem. I'll have more difficulty running my thing on a microprocessor, so reduce it. I don't want to have, so everything, so these are the options which you could be interested in. So we'll look at some of them. Okay. So what we have, so we have this cubic polynomials pi k. Okay. So if you take a point tk and I am taking an interval which is bounded by tk and tk plus 1. Okay. So the corresponding value here is qk, corresponding value here is qk plus 1, and I am assuming now that I am imposing velocities at the path points, the simplest case. So then you know the value of qk dot and you know the value of qk plus 1 dot. So you have these polynomials, you insist. So if you have these 4 equations, there are 4 parameters, so you can solve them independently for each segment. So you have n plus 1 such set of equations. That is easy. You can set q1 dot is equal to qn dot, and you know that you will get continuity of velocity because at both ends you are going to set it. So that is kind of assured to you.
So we will have n minus 1 equations.
Yes, n minus 1 system, because if you have n points, then you have n minus 1 intervals.
You said n plus 1.
I said so, sorry, n minus 1 systems of equations. So I mean, that is quite simple, and so this is what happens typically. And you can see that the behavior can be quite weird, right. So normally if I give you these points and say just join them with a smooth curve, you will obviously not, you will not take this curve, you might just pass it somewhere here and do whatever, I mean. So essentially the idea is this okay? This excursion, is this okay in the velocity? Position, it looks quite okay. But then is this okay, this cut back and dip down, and you notice here the acceleration is obviously discontinuous in the system. So to work around this, one of the commonly used systems is that you use, instead of asking the user to specify all the velocities, which is painful. I mean, I know I want to go here, I know overall time, so you let the system calculate that. So it is a fairly simple system. You define, so if I have 2 points in space, right, qk and qk plus 1, and I know this is the range and I know this is the time, so I have a velocity in that segment and I can define a linear value for that. So this is a linear velocity in the segment, or rough estimated linear velocity in the segment, which I calculate as Vk. Then what I say is that okay, you start from the first velocity being at rest. For the second one, now this is if the signs, so if both of them are going up in both segments, it is going up, then you take the velocity as the average of the 2 segments. Okay. If the velocities in the 2 segments are of opposite sign, then at the interface you take the velocity to be 0. So you don't, in that case we are saying don't take it the average of the 2 things, because this is what works better. Otherwise there is a problem with drift and couple of other things. And the whole idea is that if when you're finally stabilized, right, if an alternate input that you're getting, you are reversing signs, then you say, okay, just keep the velocity 0. Don't take it as the average of two velocities, because that then causes control instability. So this is not derived from any theoretical, any kinematic consideration. This is a practical consideration based on motor control. Okay, that if the signs in two segments are opposite sign, then you make q dot at k equal to 0. And finally, we have the final way again landing up at rest. So you just recompute this, and you get this kind of a structure coming out of this whole thing. Now in this, so this was my point, so I am going up, I am coming down, I am again going up. So at transitions, you are perennially imposing 0 velocities. Okay, so all the transition velocities are 0, however, the velocity in the intermediate points are non-zero, and you go through this. And the acceleration is obviously discontinuous. And as long as you are taking cubic, the acceleration is continuous over an interval, but there is a change here which is making it discontinuous. Okay. So once you have it in this form, the rest of the derivation is very similar to the earlier case. You are just, instead of specifying q dot k, you are essentially computing q dot k.
Sir,
Yeah.
Vk is the desired velocity at k point and dq plus 1 is the desired velocity at k plus 1 point.
Yes.
So, if
No. See, okay, let me come back to this. See, when I derive these equations, where is the equations? So basically, given this four set of equation, I can compute the equation on the segment. To compute this, I need q dot k and q dot k plus 1. Okay, the value of the velocity is the two ends. So what I am saying is if all of them are not specified, or some of them are not specified, as a estimate or a reasonable estimate of the velocity at the kth point, if the user has not specified it, you just find out what is the estimated linear velocity in that interval and the previous interval. So once you have these two values, you then say, are they both in the same direction? Yes. If they are not, take the velocity as 0. If they are in the same direction, then you take the average of the two and specify that as the velocity.
So v are the velocities in the intervals and q dot is the velocity at that particular point.
No, v is not the velocity in the interval.
V is the
Okay, so what happens is, see, this v is essentially this by this difference of these two divided by the time interval, right? But because you are doing a cubic spline interpolation, the velocity is a quadratic function. Displacement is cubic, velocity is a quadratic function. So there is a variation in the v. It is not a constant velocity. It is just a linear estimation of the velocity. So it starts from 0, ends up in 0, but then goes through a peak in this case. So you are just reverting this back and finishing it off.
What if you want to keep accelerations constant?
Keep?
Accelerations constant.
Yes, that's a big question. Then we'll have to work on it a little bit more to keep acceleration constant. So just to give you a hint, why do you have a discontinuity in this acceleration? So if I want to keep the acceleration constant, I have to compromise somewhere, right? So what I am usually going to end up doing is, I am going to come close to these points but not go to those points. So that's the strategy which I am going to adopt. Okay, is that you actually don't exactly go to these points, you come close to these points, but you don't go there, so that your acceleration stays continuous. So you will not have a jerky system, which is not a bad thing, because we expect that when the user roughly says you go like this, he is anyway proposing a rough path, and there is no reason why you cannot excurse a little bit on both sides. And if it is so critical that it exactly has to go through that little gap in there, then you better be slightly more aware of what you are programming. So then you can do much more. So that's the basic assumption. So but that's a little complicated, and in fact these you instead of path point you start calling them via points. So I'll pick it up in the next class. It gets more complicated, because what you have to do is you have to do backward chaining all the way through. So in this case what we did is we took a very simple estimation of the velocities at these points, but what we will now have to do is we have to solve the whole equation, start from here, enforce acceleration velocity continuity and accelerate and velocity continuation. So I will get equation which involves all the points and a large matrix equation which I then have to solve, which is not very convenient and is slightly more complicated, and I could not have finished it in this the next 15 minutes. So just holding it here. This is something which is very simple and does not stretch you too much beyond what you already know, except the overall concept in the context of robotics. Okay. All right.